Development of a novel ground perturbation detection model using lower limb kinematic states during locomotion. Lower limb exoskeletons have the potential to mitigate fall incidents, especially for high-risk groups such as aging adults. However, in order to be effective, these devices must detect and respond to perturbation before the user can. Challenges in applying current perturbation detection methods to exoskeleton control have hindered progress in this technology. One way to detect perturbation is to identify when the body's center of mass moves beyond the base of support, which is the area in the horizontal plane where the feet contact the ground. This area is dynamic during locomotion, making real-time estimation of it for perturbation detection challenging. Another common method involves detecting increases in whole body angular momentum, which is the combined momentum of all limb segments. This approach requires significant computational time and resources, limiting its practicality for real-time exoskeleton control. One potential alternative is to track key kinematic states, such as the center of mass and feet, as they are simple to compute, provide important insights into walking balance, and exhibit predictable patterns during stable walking. We hypothesize that a ground perturbation detector using lower limb kinematic states will outperform a whole body angular momentum-based model through faster and more accurate detection. We selected 16 kinematic states to track using reflective markers. The position of the right and left heel are monitored in 3 axes relative to the center of mass, while the COM is tracked in the horizontal plane relative to the midpoint between the feet. The velocity of each state is tracked in a global coordinate system. Our local relative coordinate system for the position states adapts to each subject's anthropomorphic dimensions and accommodates natural state drift which can occur during walking. We utilize an open-source ground perturbation dataset to develop our model. This dataset contains walking trials with 96 unique ground perturbations. Our principal component analysis demonstrates the sensitivity of the selected states to perturbations in both the anterior-posterior and medial-lateral directions. To quantify the variance of each state, we compare the current state value to its steady-state mean plus or minus 2 standard deviations. The parameter alpha remains at 0 as long as the state stays within this range. Once it exceeds the range, alpha is calculated as the Euclidean distance between the current state value and the boundary of plus or minus 2 standard deviations from its mean. The alpha value for each state at each time instance is then scaled by an inverse weighting factor to account for states with natural higher variance or those operating at larger scales and preventing their bias to the linear sum. These weighted alpha values are summed and divided by the total number of states, yielding a normalized quantification of state variance, which we call phi, which ranges from 0 to 1. We performed a parameter sweep using the open-source dataset to determine the optimal threshold value at which to determine perturbation as detected, which we found to be 0.125. Our parameter sweep rewarded values that achieved higher accuracy in perturbation detection while minimizing the delay between actual perturbation onset and detection. We conducted a pilot experiment to test the generalizability of our model and chosen threshold value on 5 new able-bodied subjects to which we induced trip and slip perturbations during walking. Here is a representative example of our phi value calculated for one of our experimental subjects. The red line indicates when perturbation was onset, and the green line indicates when our phi value crossed the selected threshold of 0.125, which means that perturbation was detected. Our model achieved 55% higher accuracy than the whole body angular momentum-based model and detected perturbation only 5% slower in the gait cycle, not accounting for computational delays in calculating whole body angular momentum. Our average model detection time was about 231 milliseconds after actual perturbation onset. This demonstrates strong potential for applications to fall prevention for aging adults, considering that older adults can take up to 400 milliseconds to respond. Therefore, we may be able to respond to perturbation before the user and apply exoskeleton control to improve balance and prevent falls. In future developments, we will address the limitations of using markers by incorporating wearable sensors to track our kinematic positions and velocities. We will also explore the use of vision to improve the accuracy of our model, and investigate how the alpha value can be used to inform the direction and magnitude of exoskeleton control required to assist a user following a perturbation.